Hello YouTube, welcome back to this series about creating a programming language with Rust. So in the last episode we created the parsing functions for all the rules in our grammar. Let's see if I can find it, all of these rules, but we didn't really write any tests, so I think I would like to do that this time. And basically what I want to do is to create some like a list of tokens that we can use as input, and then try to call the expression parser function, which should probably be public, and then that will return an expression. And that expression, we also wrote this expression to string thing. So we can call that function and check that we get the right expression tree. So yeah, that's basically it. So let's start with a test here. So test let's make a super simple one that's just this. So we need a string of tokens. So that means that we have to remember what exactly a token is. And we go here, we want to make a token struct. So we want first a token that is a number, and the lexeme should be let's say 1 to string, and the literal value we will put as well, it's an int value, I guess, so we can say 1, and the line number can be just 0. Okay, let's see if this even runs. And it doesn't run because for whatever reason it cannot like do positional arguments, which is fine. And we need to say use create scanner literal value, like that. Should work. Bunch of warnings, but the test passed. So now that was my first token. Let's actually make it just a separate variable and call it 1. And then I want plus to be another token, but the token type should just be, let me verify that this is actually a token, no, plus, yeah. So the token type is just plus, the lexeme just for consistency we'll call plus as well, and the line number is still 0. And finally we have 2, which is also a token. Like so. And now the tokens is, and we also need a semicolon, I think, right? Yes, why not? So token type semicolon, is that how it's spelled? Semi, no, it has a lowercase c, the lexeme is simply semicolon. Literal is none. Line number 0. Let's go with that. Then we have the token stream will be 1 plus 2 semicolon. Okay, so now the time has come to make the parser. So as we can see here, we simply say the parser, and has to be immutable because we're going to change things. It will be a new parser with these tokens. And then the parsed expression will be parser expression. And then we just call toString, like here. Oh, just noticed something. Very important. Then we'll say string expression is the parsed expression toString. And then we can assert on that. So the string expression should be this, I think. Let's run that. There was an error, okay, because I didn't call it, just called semicolon for some reason. And the test passed, so that's great. This was very annoying to write, so we could even just use the scanner. Let me see what it is, to produce the tokens. So let's do that in the next test. Test, what do we want to test? What do we have? We have a bunch of things. Let's do something that has a comparison. Yeah. So for example, now I just want to write the source, so we will say does 3 equal, and comparison should be passed last, so we can even do something like this. And then we will say we make a scanner at the source. Then we probably have to import the scanner too. Let me just run that, see if it works. Did it work? Okay, so now we have the scanner. Then we'll say tokens is scanner.scan tokens, and we'll just unwrap it. And then we can say new parser, basically this again. But now the string expression should be something more complicated. Namely, it should be, the last thing we do is the equality. So let me just, so I will just guess something now. Probably not correct. So it should be something like this. And it failed. Okay, that's interesting. So there actually is a bug in this toString code as well, where it seems like it doesn't have a way to treat the equality operator. Operator.lexi. Okay. the operator is a token. So that's very interesting. So it looks like the lexeme for okay, so which token will it be? 1, 2, 3, 4. So 3, yes. Don't see it anywhere. Let me just put this. Yes, so the lexeme doesn't get set, so there's actually a bug in the scanner. That's great. Okay, so we have here match equal equal, and then we say hi. That's very interesting. So it's relying on this thing, which I will just try to print. Try another one. Try yet another one. So for whatever reason, it's not really setting the lexeme correctly. That is annoying. Okay, so let me look at start and current. It's interesting. They look correct. This one has 2 in it, which is also correct. Can I just do this? Oops. Compiled, but what did it do? Okay. Lexeme is still not set, but at least it's the correct values. Because of course it's not set. This is interesting. So this did not work. I wonder why. It's probably that the map was never consumed. Okay, fantastic. Now it works. Let me go back to the scanner, just check there's no print. those can go away, and there we go. Okay, so that seems to work, and I am satisfied. But let's keep going a little bit here with the book. Okay, so we are getting into some new territory, namely how to handle errors. And there's a bit we need to think about. So the first thing is that we've just been throwing an exception when we reach an error here, for example. But really that's not so nice, because if there is some kind of error, we don't want to just quit parsing altogether. Rather, we want to like recover nicely and maybe even keep parsing, so that there's an error in one line, but we still parse the rest of the lines and try to like see if there's any errors there, so the user can see all the errors that are happening at the same time. So we don't want to just panic. We want to rather have a result type here, I think. And, you know, similar to the scanner. And we will actually use the same result type. And now we just want to apply this to everything, first of all. There we go. So now so this comparison will also return a result. And for now, we just want to propagate the error all the way up. So I will add this thing, and same here. But if we get all the way here, we will return OK. And same here, same here. Now the point later will be that sometimes we don't want to just return the error as we do here, but we want to just store a message somewhere that tells the user what could be wrong, and then keep parsing. So again, pretty much the same pattern. Oops. Okay. Don't need the question mark there because it's already turning an error. We don't need to return early, so to speak. And now this consume thing should return, let's say, nothing or an error. So here we will go and we will say we will say it's an error with the message to string. And it will be an OK, and it will be an OK. Let's see if that broke anything. And it did. Line 128. Peak is now a problem. Okay, I don't get that, so let's... okay, so we just need to return OK here. And oops, that was fine. Let's also just try to run it for good measure. No, so that didn't work. Right, so the tests are broken. Now we will just unwrap it, because this shouldn't produce an error. Run it again. Okay, and we're back on track. So now we are propagating errors instead of just panicking. That's good. And now in the book they're talking about what you do when you encounter a syntax error. So what you do is you want to report it and you want to start parsing again, but you cannot just start parsing again right after where you encounter the error, because that will probably just lead to more errors that are not really there. So what you do is you move to some point where you think you can start parsing again. And that's called synchronization. And the way that we will do it here is to move to the next semicolon or the next statement keyword. So at some point, not now, we will use this, and it will simply advance let me write it. So we'll advance until we see a semicolon, then we stop. Or if the one we're at now, the type of that is a class, function, variable, for, if, while, print, return, then we will also return, otherwise do nothing. And finally we just advance here. Let's check it. There is an error because it should be a comma. Found tuple. Okay, so how is it like this? Perhaps it's just this. Or a vertical bar to measure multiple alternatives. Okay. No, let's not do that. Let's do it like this. Okay, great. So let's see how, I just noticed something when I was reading here. His consume thing, he still throws the error. Whatever. Okay, so it discards tokens until it's found a statement boundary. After catching a pass error, we'll call this, and hopefully we're back in sync. When it works well, we have discarded tokens that will likely cause cascaded errors anyway, and we can now pass the rest of the file starting at the next statement. We don't get to see this method in action, not yet. We'll get to that in a couple of chapters. For now, if an error occurs, we'll panic and unwrite all the way to the top and stop passing. Yes. We also have that. But we could hook it up here to the main. So right now in our run function, which is like the key to everything, we just scan the input and then we don't do anything with it. So we can make a parser and call new on the tokens, and then we won't print those, but we will print yes, we will print the, so we will say, what's the main function again? It's expression. So we will call expression. We will return the error if it fails, but if it doesn't fail, we will just do this. Amazing. Now we could check it. Anyway, let's read a bit more. We're mostly done parsing expressions now. There is one other place where we need to add a little error handling. As the parser descends through the parsing methods for each grammar rule, it eventually hits primary. If none of the cases there match, it means we're sitting on a token that can't start an expression. We need to handle that error as well. So let's go to the primary. Okay, so yeah, if there are left parentheses, then we do something. This is interesting. Why did I put this thing? Right, so this is why. Okay, so all of this stuff is wrapped into this thing. And what is he saying over here? He's saying, okay, so if it's false, true, nil, number, string, then we turn it into a literal. Otherwise, if it's a left paren, we do this, but in any other case, we throw an error. So let me think about this. There's also some weird behavior because match token advances. at least sometimes it advances the counter, or the well, okay, it advances if it's found the one it's looking for. So I guess that's okay. So actually up here we could say, it's not nice, but we could say, like, we could do something like this. Okay, if it's false, then we do this. But I was trying to get away from that. Because there's this logic in the match token thing, we cannot use the Rust match statement, which could be a sign something's wrong. So let's try this. First we will peek, and let me just see what the return type of peek is. It is a token. So okay, whatever. And then we will match the token type. And if it's a left paren, then we will do all of this. Yes. If it is false, true, real, number, string, then we will do this. Yes, good. And just for now, I'll add panic here. Comment this out. Format. Okay. That is great. And now we should be able to do this. Where if it's anything else, and now it's also a little bit more extensible. I want to do this. Okay, so otherwise we do error, expected expression, and this one we will just return. And down here we will need to advance, because if we get here, it means we correctly matched on a token, and we need to advance the pointer to consume it. And then finally we'll just return the results. Let's try that. And by try I mean run the tests, and that didn't work. What is the string val? Okay, scanner string. Okay, string lit. And this thing has to be to string. And these guys have to be results. There we go. Oops. No errors. Tests pass. Everyone's happy. Okay. How about in the expression? Shouldn't really have anything to do with, and it doesn't, so that's good. Okay. With all that all that remains in the parser is to define an initial method to kick it up. That method is called naturally enough parse. If you say so, I will make this one not public. I will make a parse function. It will return a result type, and it will simply for now call into the expression function. And down here, we will call parse instead. Wabam, there's an error. 24. In main. No method named, because for whatever reason it was parsed. Okay, and it's working again. We'll revisit this method later when we add statements to the language. For now, it passes a single expression and returns it. Great. We also have some temporary code to exit out of panic mode. Well, we have a different way of dealing with that. Syntax error recovery is the parser's job, so we don't want the parse error exception to escape into the rest of the interpreter. Sure, we can always prevent that by catching the error here. It returns null. We return an error type, which is better. That's okay, but we do it better. Parser promises not to crash or hang on invalid syntax, but doesn't promise to return a usable syntax tree. Finally, we can hook up our brand new parser to the log slash and try it out. Still, we don't have an interpreter, so for now we'll parse to a syntax tree and then use the AST printer from the last. Yes, exactly. So let's see if we can run this thing, and produces a ton of errors, but those we will ignore for now. That worked. That worked. That did not work. That's very interesting. And it was with a stack overflow. So obviously we need that case in a test. Test actually this I can do, so that's very good. So test equality with paren. So yeah, 2 plus 2. Everything is the same. I expect this to be the result. Or maybe I expect this to be the result. Let's run that. It will fail with Stack Overflow, which is good. So let's try to see if we can diagnose it. So we call the equality. It will pass the left side correctly. It will get the operator. It will try to get the right side as a comparison. But then does it support equals, like several equals? We'll just ignore that for now. So it will try to pass the comparison, that will try to pass it as a term, which should work. And then when it passes it as a term, this thing will, let me try something. Or rather, let me try it a better way. Let me see if it can even pass things. So it cannot, so it's in the passing itself that it happens. Let's go back up to the comparison. Okay, so we'll go here, try to pass it as a, it will go here, sorry. Try to pass it as a term, and then it will succeed, and it will be kind of at the end of the file, so this one should not trigger. Then we'll go here, same story. We'll go here, here, here. So this is what should happen. It should, okay. So we need to advance before we try to get the rest. And same thing here, right? We'll just add it there. Now, let's see what happens. It worked. It didn't stack overflow. Okay, fantastic. So the problem was just that we didn't advance the pointer, so it when it like called this expression, it ended up back here again. And then it saw that the token it was looking at was the left paren, the same one, and then it's, you know, infinite loop. So cargo run 1 equals 2 plus 2. What happens if we say 1 equals 1 equals 2? That just worked. That's amazing. 2 plus 2 times 3. 2 times 3 plus 2. Okay. You crossed the threshold. That's really all there is to handwriting a parser. We'll extend the grammar in later chapters with assignments, statements, and other stuff, but none of that is any more complex than binary operators we tackled here. Yeah. Okay, I think we'll leave it here for now. And in the next episode, we will start evaluating expressions. Which, if I'm not mistaken, it will basically take these syntax trees that we can now generate, and instead of just printing them out like this, in this Lisp form, it will actually evaluate it and return a value. So when we write 1 plus 2, it will not do this, it will return 3. But, oops, that is a story for another time.